Okay, this is lecture 10. ECE 2029, and today we are doing memory elements. What we have done so far is we have seen the structures that do not really have memory. Okay, no memory so far. We started with transistors. Then we put them together into gates. When we talked about methods of doing gate level design, such as Boolean. And then we said Boolean, we need something a little bit more systematic, and we looked at Carnot maps. And then we came up with expressions. And then we did Verilog. And then we also did packages, something like multiplexers and things. And if you look at all these circuits, however they're represented, they look like a box with some inputs, let's say A, some output, let's say W, and some functionality. And the thing about it is the function of the output is and the output is a function of the input. And we call these circuits combinational circuits. Combinational circuits are those that have a circuit which is reactive to its input, and then as soon as you change the input, the output changes. Maybe there is a delay, but then you can count on it. If you come in tomorrow and this circuit is still working, you give it the same input, it comes out with the same output. What it means is that it has really no memory of the past. It has nothing remembered of what has happened to it before. What we do today, though, is we talk about elements. For now, I call them memory elements. And then again, we start like we started with transistor. We build gates. We take these memory elements and make them more sophisticated memory elements. Okay, and so more complete, let's say, memory elements. And then once you are happy with the elements, like we were happy with the NAND and NOR and all of that, we will come up with a procedure for designing with these memory elements. Then we will go back to things like Carnot map to design them, but then we show some like I said, procedures like state diagrams and things for describing them. But then when we use these state diagrams, we will still go back to Boolean, and we will still go back to the Carnot maps for complete design of the memory elements and the gates and a complete circuit. And we will also talk about some packages. We will talk about things like counter. Counter is obviously a package that has memory, meaning that it remembers its previous count, and the next count is based on the previous count. And therefore, it is important that it keeps its old value. It means that it has memory. So we also talk about packages. And then we also, of course, show Verilog description for various components. But see, the difference between the circuits with memory and no memory is that if I want to do the same block like this, it has certain inputs, it has a functionality, okay, and then it has certain outputs. And then this is what happened. You come in and apply to it some input today. Okay, you think that the W has to be f of A. Okay, W has to be f of A. Okay, but then you come in and apply some input to it today, like AI, and you come up with WI, W today, and then an hour later you apply the same exact input, AI again, but then you see that your W is not the same as the 2 hour ago output. Then you come in and give it another 1 minute and then apply another input to it. Then you find that, well, this output is also different. What it means is that I cannot just say that I cannot just say that W is a function of the input. W is not necessarily a function of the present input. Okay? And this is what we are dealing with right now. Okay, so I just write here that not necessarily. The kind of circuits we were dealing with before is called combinational circuits, and the kind of circuits we are starting to talk about are called sequential circuits. So these are sequential circuits, and now we'll be talking about the sequential circuits, and we'll be talking about the boxes. Let's do this. The boxes that have certain inputs A, certain outputs W, and there are more than one function inside, which we'll be talking about here. Alright, so this is how I think about this sequential circuit. So let's talk about sequential circuits. This is how I talk about sequential circuits. I say that actually it's not all that bad. If you look at W is a function of W of I, that means present W, today's W, is a function of input today, input yesterday, input day before, input day even before. Okay? Or maybe many days before, depending on really how much memory it can keep. This is really hard to keep track. It is difficult to say that, okay, I need to remember all these inputs, and whenever I want to calculate an output, I will have to take all these inputs into account and then come up with the output. I'm going to look at it differently. I'm going to say that W of I is a function of the present input, and then I will combine all of these, or accumulate the effect of all of these inputs into the present state of my circuit. So my W becomes a lot easier. I say that my W is the function of the present input and the present state of the circuit. But see, since A came in, or a new A came in, obviously that's going to change the state of my circuit. So the next output has to be a function of AI plus 1, and then all of the AI minus 1, all the way down to the time the circuit was created, or to the time that the circuit remembers. So this is what I'm going to do. I'm going to say then state of I plus 1 is a function, a different function of the present input and the state of the circuit. So what I really have is a combination of two expressions. Okay, two expressions that together will decide that my output becomes such and such, and then my next state becomes something that I will be using it for the next time. If you think about the circuit carefully, this is what I'm getting. I have a circuit with certain inputs A, with certain outputs W, and then there is this state of the circuit, whatever number of lines it is, I don't know yet. Okay, I even haven't talked about the number of inputs and output, but then there is the state of the circuit which feeds back to the input of the circuit. So what it is really the circuit has a function in terms of the present state and the input, which decides on the next state of the circuit, and it also has another function which decides on the output of the circuit based on the present state and the output of the circuit. So I'm going to do this. I'm going to say this is my function f and this is my function g. Okay? And therefore, if you look back, you see that down here I said that my sequential circuit has two functions in it, one deciding on the state of the circuit, and I'm calling this one my present state. This becomes the next state of the circuit. Actually, at all times, the next state is what becomes the present state for the next set of inputs. Okay, so these next state and present state are only different in time, which we will define the timing later on. And then, like I said before, f is or w is a function of ai and state I, and state I is a function of ai, comma ai. I'm sorry, it's I plus 1 is this. Then the state is really, remember I said that, going back here, I said that accumulation of all of these inputs is the state of the circuit. But then how much accumulation of all these inputs? How far back do I go? Okay, well, I go as far back as my circuit remembers. That means a circuit with a lot of states to remember is a circuit that remembers a lot of information. Okay, but then some circuits are not required to remember a lot of things, and therefore what I decide is, look at these number of lines here in my binary system. I say that any number of feedbacks that I have, the number of things my circuit remembers is maximum 2 to the number of feedbacks, number of lines that are being fed back. And this is obviously clear, right? If you have 3 lines here, that means 0, 0, 0, all the way to 1 1 1. That means your circuit remembers, or can distinguish between 8 different states in addition to whatever the input is. Okay, and therefore I say that my circuit is okay. It has 8 numbers that it can remember. All of this is good, and now what I have to do is to actually build a circuit. Okay, the circuit I'm building is a circuit. Now that I have shown you that I can build memory by feedback, I'm going to make one feedback line here, and I'm going to build this circuit. This is going to be my output, which for now I'm calling it Q, and this one is my feedback line, which I'm calling it Y. Okay, look at the circuit to the left. This is very similar to that, right? It has 2 inputs, and let me make it a little bit more like that. It has 2 inputs like this. Okay, and then it has the feedback, which in the circuit on the left I have 2 feedback. The circuit on the right I have 1 feedback. I'm going to redraw this circuit slightly differently. The only reason I redraw it is because people are accustomed to that. I guess many years back somebody showed it this way. People liked it. They called it cross-coupled NOR gates, and still being referred to as such, cross-coupled NOR gates. So still I have a R input, I have a S input, and then I have this Q, and then for now I'm calling this Y. What I like to do is the following. This is a circuit with some feedback. Okay, so it tells me that okay, somewhere I have some kind of memory. Okay, I want to exercise this. I want to make sure that this does have memory or not. I start with a value 0 on R, a value 0 on S, and of these 4 signals you see, R, S, Q, and Y, I have to decide on 3 of them, and then I decide on 0 here. Okay? By the way, let me say something. This is also a circuit with feedback. And of course this has memory. You know why it has memory? Because if this is 5 nanoseconds delay, you put a 0 here, this is 1. Okay, now it remembers that 5 nanoseconds ago it was 1, so it toggles, now it becomes 0, and therefore this is a circuit that oscillates. You put more inverters, the frequency of oscillation becomes smaller, the period gets larger. But then the difference between this circuit and the circuit I'm showing on the left here, or the cross-coupled NOR gate here, cross-coupled NOR, and the circuit on the left, or the cross-coupled NOR, is that the circuit on the left is stable, the circuit on the right is not stable. But then how can I prove that it is stable? Well, let's do this. Let's say I put a 0 on the Q, a 0 here, a 0 here. I propagate the values. If the propagation of the values come up with a value that does not change, then I say, okay, this at least this combination of inputs is puts the circuit in its stable state. And so let's look at the NOR gate at the bottom. I have a 0, I have a 0, and therefore the NOR of them is 1. Let's look at the NOR gate at the top. I have a 1 on the lower input of it. Here I have a 1 on the lower input of it, I have a 0 on the upper input of it, and the output is 0. Once the output is 0, I'm going to take back that 0 back to this gate. I say, well, a 0 here. Well, a 0 is a 1. So my circuit is sitting stable, very happy. So what it is is I started with R of 0, S 0, Y 1, and Q 0. Okay. A few nanoseconds later, what I like to do is, I'm sorry, I have an error here. This is S, this is R. S is the one on top. That's the one that lines up with Q. Actually, the only reason I did this crossing over here at the inputs is that I wanted the S and Q to line up with each other. Okay, this is what I'm talking about. See, S and Q are lining up, R and Y are lining up. I like S and Q to line up for reasons that you will see later on. After a while, what I'm going to do is I'm going to change my S to 1, keep my R 0. I'm going to study to see what happens. So my S has changed to 1, my R remains 0, and then the 1 on S propagates in the lower NOR gate. Now I have a 1 on the input, I have a 0 on the other input. That doesn't matter. A 1 means that this becomes a 0. A 0 on Y feeds back to the gate on top, and now I have two zeros on my NOR gate, and therefore this becomes 1. So what is happening is, after this change, after a little bit, Y becomes 0, and then again, after a little bit of time, Q becomes 1. Things go on with no change for as long as I haven't changed anything, until I make another change in my circuit. This time I change S to 0, and then keep my R back again to 0. So S is changing to 0, and then I'm going to propagate the 0 into the lower NOR gate. I find that actually the 0 and a 1 still keep my my Y at 0. Okay, and then the 0 on the upper gate and a 0 on the upper input of the upper gate keep my output to 1. Okay, so what it means is, even though this became 0, no change happens here. This is going to continue until I start doing something different. I'm going to keep this 0. I'm going to keep this 0. But then I'm going to put a 1 on my R. I'm going to put a 1 on my R. R becoming 1. The upper input of the upper NOR gate is changing, and therefore I have a 1 on its input. I have a 0 on the other input of it, causing the output to become 0. The 0 on Q feeds back to the NOR gate with Y output, and then I have a 0, and I have another 0 on it, and therefore this becomes 1. So what it means is, even though I didn't change R, okay, my oops, sorry, I did change R. Okay, I change R, and then changing R causes my first changes my Q to become 0 after a while, after some delay, and then after that delay my Y becomes 1. This continues for some time, until at a later time I keep this 0 and then change this back to 0. Changing R back to 0 affects the upper input of the upper gate, and therefore I will analyze that. I have a 1 and a 0 causing the output to stay 0. Okay, so this is what I done. I brought my R back to 0. And my S remains 0. And then my Y for now doesn't change. My Q becomes 0. Okay, means that no change. Since Q is 0, I have a 0 on S, and then my Y remains at 1. Okay, I'm claiming that this is memory, and I have proven that this is memory by this diagram. Let's look. Here I have a situation where my S is 0, my R is 0, and the output is Q. Don't look at Y for now. Here I have a situation where my S is 0, my R is 0, but what is my I? Oh, my Y. My Y is a 0. I'm sorry. My Y, what is my Q? My Q is a 1. Okay, and then I'm looking at this situation again, and I find the same exact thing as the original case. Let me change some colors here. Okay. Here, in the first orange, S is 0, R is 0. Let's look at Y. Q is 0. In the green area, S is 0, R is 0. And look at my Q. My Q is 1. So what I'm really seeing is that for the same set of inputs, in one case my output is 0, in one case my output is 1. Let's look at it here again. This is 0. This is 0. My output is 0. What it means is, in one situation, with the same inputs, my output is 0. In another one, with the same input, my output is 0. What has caused this? What has caused this is, obviously, things have happened to my circuit that my circuit remembers that. Now look at Y. See, in one situation, in this place here, my Y is 1. In this situation, my Y is 0. What it means is, and Y is the state of my circuit. What it means is, based on the state of the circuit, if inputs are 0, 0, the output, if my state of my circuit is 1, my output becomes 0. And 0, 0, if the state of my circuit is 0, my output is 1. And then what changes this state of the circuit? If you look carefully, you find that what changes the state of my circuit is a pulse on S, making the state of my circuit always a 0, or a pulse on R, making the state of my circuit a 1. Instead of looking at the states, let's look at the outputs. The outputs are like this. If I give my circuit a positive pulse on S, my output becomes 1. If I give my circuit a positive pulse on R, my output becomes 0. S is for set. R is for reset, and I just build a set reset latch, a circuit that latches whether the last pulse came in on S or the last pulse came in on R. I look at the output, I find that my output is reset, so I say, well, the last pulse must have come on reset. I look at my output, I see a 1 on the output, then I say the last pulse must have come on the set input. And then I look at Q and Y, I find that anytime Q is 0, Y is 1. Anytime Q is 0, Y is 0. And therefore I say I don't need a Y, don't need a Q. I just call this one Q bar. And for that matter, I can use either one of these for the output of my circuit. Okay? I can call one the output of my circuit, and that's why the cross-coupled notation helps you in this case. You can call one of them your output, the other one the feedback. Whichever you pick. Alright. So, I just built my first memory element. And let's do this. Let's write down what we have come up with. I came up with a circuit with an S and R input. Let me write these in lowercase because at one point I will make them uppercase. And 0, 0, 0, 1, 1, 0, 1, 1. I showed that the next output of my circuit, if set and reset are both 0, the next output remains the same, it doesn't change. If my reset becomes 1, the next output becomes 0. If my set becomes 1, the next output becomes 1. And then there is something about this. If I remember how I explained this, I said that Y, the value of Y, is the one that keeps the state of my circuit. Actually, the two being different, the Q and Y being different, that's how the state of my circuit is kept. If I give my circuit S and R 1, 1, what happens is, if my Q is 0, my Y becomes 0 also. Actually, what happens is that my circuit forgets about whatever it has remembered in the past. And therefore, this is a no-no state for me, or a no-no input for me. This table is it looks like a Carnot map, but it's a truth table, but it's not a truth table. It's a transition table. The difference between the transition table and this table here is that this table between a transition table and a truth table is that a truth table has the present output. Okay, like for example, you said I have A, B, W, 0, 0, 0, 1, 1, 0, 1, 1. You say 0, 0. Let's do an XOR, for example. Okay, this is a truth table, and notice that the W here is the present value, but then a transition table, the output is the next value of the output. Timing is involved in the transition table, as it says transition, but then timing is not involved in truth tables. All right. So we just build our own first memory element, and now let's see if this is good. This is enough of what we need. So I'm going to take that gate, cross-coupled NOR gates, and there's an S, there's an R, there's a Q, and there's a Q bar. Even though I claim that this is a memory element, but it is a little bit difficult to convince you this is a memory element. Yeah, it does remember something. It does remember a pulse on S or a pulse on R. But it's far from what we like to call memory. What do we like to call memory? We like to, for one thing, when we want to call something a memory, we want to have timing involved. Okay, so we want to say, well, if set is 1 at the time such and such, I like the structure output to remember it as a 1. And then when I talk about reset, I said at such and such time, if it is 1, then I want it to reset. But this component has no concept of timing. I mean, timing is implied there by S and R, but I like a different signal here so that I can impose my timing on it. Okay? So this is what I'm going to do. I'm going to build a circuit like this. Again, a cross-coupled NOR. Okay? If you want to be a little bit more accurate, when you cross this, okay, and then the inputs the same thing, they're crossed like that. Again, the only reason I like it to be crossed is because the set input sets the Q, and therefore I like them to line up. And then I'm gonna put a an AND gate here, an AND gate here. This becomes my external S, this becomes my external R, this becomes my internal S, this becomes my internal R, and then I'm introducing a new signal here, calling it C, or my clock. I'm claiming that this structure now has timing associated with it. Okay? What it means is this. This structure remembers whatever was on the capital S and R at the time that I clocked my circuit. At the time that I put such a pulse on the clock input of my circuit. And then whatever happens to S and R outside of this circuit, or the capital one, whatever happens, the circuit completely ignores until the next time I put a pulse on the clock. Okay? So this means time 1, this means time 2, and so on. So indeed, with this clock, I introduce some timing into it. And therefore, the S and R, the external S and R, if they are the external S and R, if they are whatever they are, they're not gonna affect my circuit unless there is a clock pulse. I'm gonna redraw the transition. Let me do the transition table of this. This is S R Q plus 0 0 0 1 1 0 1 1, and we said this makes it no change, this makes it 0, this makes it a 1, this is a no thing. Okay, and then for this circuit, my transition works like this. S, R, these are the outside ones, Q, S, R, lowercase on the left circuit. And then I say I have a clock. If the clock is a pulse, then 0 0 have no effect, and the output becomes whatever it was. Sorry, the one on the left, it has to be 0 cube. A pulse on clock 0 1 resets it to 0. A pulse on clock 1 0 sets it to 1. Only during a pulse on clock 1 1 is a bad state, is something I should not do with my circuit. Okay? The introduction of this clocking thing gave some timing to my circuit. So this is how I say it. I have a time input, and that time is when I look at my inputs. So at the time of whatever the input value, at the time of a clock, I will pick up the S and R, and if S is 1, I will set my circuit. If R is 1, I will reset my circuit. But see, I try to make this a circuit that remembers something. The problem I have is that I do remember the S and R, but still, it doesn't match with what you and I like to think of memory. What do we like to think of memory? A memory is one that keeps, let's say, a number between 0 and 15 at the time of such and such. And then until I tell it to override this output, it's not going to override it and it still remembers it. Okay? Or maybe I should have said, unless I tell it to override it, it's not going to override it, and it remembers it until I say, well, now you can override it. Or remember this new number. I set the example 0 to 15. Let's now change it 0 to 1. I want to build a circuit that remembers a number between 0 and 1 at the time of the clock, and then until I give it another clock, it's going to remember that number. What if I take this circuit okay, still the same circuit. Take the circuit, and then I say the upper input sets it, the lower input resets it. I either want to set it or reset it. Okay, so there is really no point in having two input set and reset. Why don't I just put the complement of these in here and then make it a D input? What it means, if you look at the table on the left hand side, is I have a C input, I have a D input, I have a clock, and only those situations that S and R are complement of each other is gonna work here. Is gonna appear here. It's gonna exist here because I put an inverter in between the two. Okay, what it means is let's look at the this situation, and this situation still exists. Okay, these two situations still exist, which means that, let me use different color. This exists, And if I'm not giving it a clock, then this also exists. But then the thing is, the 1-1 situation will never exist. Look at the circuit on the upper right now. See, if D is 0, clock is 0, well, the internal S is going to be 0, the internal R is going to be 0. If D is 1, clock is 0, same thing. If D is 0, clock is 1, S is becoming a 0, R becomes a 1. If D is 1 and clock is 1, S becomes a 1 and R becomes a 0. That means these three colored situations do exist, can happen. But then the bad one, the 1-1 case that I said that it loses my memory, will never happen. Okay, so that's a good thing that happened. But then the better thing that is gonna be gained by this circuit is the following. My Q plus, if D is 0, during the time of the clock, my Q plus is 1. If D is 1, during the time of the clock, my Q is, my Q is 1 if my D input is 1. What it means is whatever was on D at the time of the clock is kept, is saved, is memorized in my output. And then, what if I don't have a clock? If I don't have a clock, whatever, that means it's a 0. Whatever is on D, 0 or 1, doesn't matter. Q goes into the output. That means my output keeps its value. Okay? And notice that the three situations I was showing here, the 0-1 is implemented by this. Okay, D is 0 means R, the internal R is 1 and the clock goes through and makes the output 0. The 1-0 is implemented by this, and the situation that my output doesn't change is implemented when my clock is not active. Means this. This is going to be called from now on a clocked. Let's do this first. SR latch. This one a clocked D latch. Okay. And this is an unclocked SR latch. Or simply a cross-coupled NOR structure. I like this structure so much that I give it a name, which I did. I give it a symbol C1 1D. Okay. One on the right hand side is the same number used on the left hand side here. Okay. When I use a number on the right hand side, that signal is controlling. And when I use a number on the left hand side, that means whatever signal is controlled. And this is exactly according to the definition that we talked about, which means that the input is controlled by the clock input. Okay? If you have a more complex circuit, meaning that you have two clocks, maybe two inputs, maybe, and then you can use number 1 for controlling number 1 input, number 2 for controlling number 2 input, or you can combine them, saying 1 comma 2, meaning that this input is only affected when both clocks arrived, or something like that. Okay, but in any case, numbers on the right hand side are for controlling signals, numbers on the left hand side are for controlled signals. Some of the properties of this, and that is this circuit is transparent. What does transparent mean? See, transparent means this. Look at the, I'm going to put some numbers, some values here. If my clock is 1, D changes, goes from 0 to 1, 1 to 0. According to the table I have, if the clock is 1, a 0D transfers to the Q, a 1D transfers to the output. What it means is the Q output follows whatever happens on D. Okay, so it's transparent. It's like as if it doesn't even exist. D changes, Q changes, for as long as Q is 1. And that's why this circuit is also called a transparent D-latch. Okay? Transparent D-latch. This circuit also has a characteristic expression equation, and that is Q plus equals D. Remember, plus I'm using for timing. That means the next value of the output is whatever the present value of the input is after the clock. And that's how I'm interpreting this plus over here. Alright, what else do we need to say about this? The one in the middle, this is also a clocked SR latch. And if you want to know exactly how that works, look at it this way. S R Q bar 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. And 0 0 0 Q plus is 0 0 1 is set. This is no good. 1 0 0 1 0 1 is 0. 1 1 0, that means Q is, let me show a tiny line here. Okay. This is no good. And 1 1 0 sets it to 1. If I turn this into a Carnot map, SR00, Q0, and Q1 that remain the same. 0 1 always reset, 1 0 always set, and 1 1 doesn't change it. And therefore Q plus is S ORed with R bar Q, and this is the characteristic equation of the SR latch, or the clocked SR latch. How about the very long description of it? This is the very long description. This is a I'm going to be using an always statement. The always statement is sensitive either to D or to the clock. It means that if D changes or clock changes, there is a possibility that something happens. And then I look. If clock is 1, then Q gets D. That's all there is to it. Remember that if Q is the output, you have to declare Q as reg, because it's being used on the left hand side of an always statement. And for the clocked SR latch, the same thing. And then we'll be doing more Verilog, but now that I showed you the symbol and everything, and this is the Verilog for this design, or this block diagram, or this, or this, or this. Of course, you could write down the gate descriptions using assigned statements and wire them like what you are seeing there, and that would still work the same way. Okay, but then for memory elements, we usually use always statements because it's very descriptive of how they behave. See, look at let's read the always statement. It says if D and C D or C changes, flow begins. When flow begins, look at the value of C. If C is 1, D goes into Q. What if C is not 1? It says nothing. When it says nothing, it means that it retains its old value, which is exactly what I expect from a latch, from a memory element. Alright. I feel like this is a good thing. Okay, and so maybe we are at the end of our road and saying that, okay, we have already achieved what we wanted. Okay, maybe not. Let me design something. I'm so happy that I have this circuit and I want to design something. The circuit I want to design is this: a circuit that with each clock pulse it increments, and I want to make it a 4-bit circuit. So if it is the value, let me write it down here. If the present value is let's say Q3, Q2, Q1, Q0, Q3 plus, Q2 plus, Q1 plus, Q0 plus. If it is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. Okay. Zero after a clock becomes 1. 1 after a clock becomes 2. 2 becomes 3. 3 becomes 4. 4 becomes 5. 5 becomes 6. 6 becomes 7. Okay. 7 becomes 8. 8 becomes 9. 9 becomes 10. 10 becomes 11. 11 becomes 12. 12 becomes 13. 13 becomes 14, and 14 becomes, that's not the end yet, 15. 15, 1, 1, 1, 1, rolls back to the beginning to 0. This is the circuit I want to build. So this is how I'm going to build it. I'm going to say I'm going to build a circuit. I'm going to build a circuit, a combinational circuit. Okay. That is an increment. And then I'm going to build a circuit, a memory circuit that holds the value. Okay, the memory I already know how to build, and I'm going to build this circuit. Just repeating the same thing we did in the previous slide. Then there's a clock. Okay. This is my Q0, Q1, Q2, Q3. The inputs are the present values. Then a pulse on clock happens. What happens is whatever number is here, let's say 1, 1, 0, let's say 1, 0, 1, 1, which is 11. I didn't like 11. Let's say 10, 1, 0, 1, 0. Okay, I wanted a number that doesn't look binary, so let's say 8. Okay, 1, 0, 0, 0. 8 is here. Clock ticks. 8 goes here and goes into the output. Okay, 8 goes here. Then I'm going to take these outputs, feed them back into the circuit. And then the 8 that was sitting here, the 8 that was sitting here on these outputs is going to feed back through the yellow part of the circuit, which is the incrementer, and therefore that becomes 9. Okay, so 8 comes here on these inputs. It's incremented, it becomes 9. By the time it reaches on the input of the green part of the circuit, my clock should be 0, and therefore my circuit still keeping its 8 until the next pulse. The next pulse puts 9 into the output of my circuit. The next pulse put 10 into the output of my circuit. Okay? That looks fine on paper, and before I say what the problem is with this, let's do the circuit on the left hand side in the yellow area. That's an incrementer. An incrementer is a full adder for now, full adder. Remember we said that full adders from last time, we said that the carry out goes here, carry out goes here, carry out goes here. Okay, and then we said we have a carry in. I'm gonna put the 1 in the carry in, and then this is A3, A2, A1, A0, and then for B I'm gonna put zeros here. If I put zeros on one of the inputs of the full adder, let's look inside the full adder. Inside the full adder looks something like this. A, B, carry in, and this. If B becomes 0, I don't need this XOR gate, and A goes directly here. If B becomes 0, I don't need this AND gate, and I don't need this AND gate, and this goes to the output. Okay, and therefore this becomes this circuit. Okay, the very rightmost bit is 1. This is actually, we have talked about this before, this is a half adder, and therefore if I replace each one of these full adders with half adders, that is an incrementer. I'm gonna build that incrementer right over here. Let me erase these numbers here. Okay, I have this one. For now I am not touching it, and then I have this XOR. I have another XOR, then an AND gate coming into this, an AND gate taking these, coming into this, Okay. Now I have another AND gate, which, if I really want to use full adders, that generates the carry output, which I'm not using it. And for now I'm going to put a 1 here, and now let's analyze this circuit. The circuit works, the circuit works supposedly as an incrementer. Let's say at one point in time, I have number 8 on these inputs. That number 8 gets incremented by this array of half adders and becomes 9. Then I give it a clock pulse. As soon as I give it the clock pulse, 9 comes in and gets stored in here, and now I have a 9. Okay. Now 9, the blue 9, is going to go back, feed back, replace the 8, the green 8. Okay, so I'm going to get a 9 here. And that blue 9 is going to come in here, pass through the incrementer, and it's going to become a 10 here. By the time it reaches at this point, hopefully my clock is 0, and this is as far as it goes. It sits right there until I give it another pulse. That pulse takes the blue 10 and brings it into the circuit, makes this 9 a dark blue 10. The dark blue 10 now goes, replaces the light blue 9, and then automatically, without me controlling it, it becomes 11 sitting here. And then 11, after the next clock pulse, goes into this and becomes, let's say, a black 11 sitting here. So looks like it works as an incrementer. But let's go back and look at something here. Remember I said this is transparent. What it means is during the time that let's use this. During the time that my clock is 1 here, these 4 structures, all of them are transparent. It means that whatever is here goes here, whatever is here goes here, whatever is here goes here, and whatever is here goes here. Not only that, whatever is here feeds back and reaches here. Same thing with this. Same thing with this. And same thing with this. What does that mean? What it means is if I keep my clock on too long, these blue lines are gonna feed back, go through the incrementer, 8 becomes 9, and then 9 goes through the incrementer, clock is still on, and then 9 goes through the register because it's transparent, or through the latches because it's transparent, becomes 10, 10 goes back, so 9 becomes 10, 10 becomes 11, 12, 13, 14, 15, 15 becomes 0, and then it keeps oscillating. Unless I know exactly when to stop it. unless I let only one propagation go through and then stop it there. Now, the reason for oscillation is because it is transparent. Because the input sees the output, or the output sees the input, whichever way you want to look at it. So there's nothing I can do with this. Okay? Unless I keep my clock exactly short enough so that only one propagation goes through. The problem with that is maybe I started my circuit and the gates are not warm yet, so they have some kind of delay. And I adjust my clock according to that delay. But then later on, the circuit warms up and then the delay of the circuit is less. And therefore, I get 2 propagations, 3 propagations. Actually, I cannot design a circuit like that. I cannot design a circuit and adjust the clock according to the room temperature or the heat of the circuit or the or the length of the wires or the capacitance of the wires. This circuit will never work. Actually, if you build it in a laboratory, it will be very, very difficult to get it to work. Okay? And if you get it to work now, then a few seconds later, it's not going to work. So even though this looks pretty good as for a counter, but it doesn't work. How can I resolve this situation? Remember, I have the transparency problem. How can I resolve this situation? Well, let's look at another situation that we have transparency, which causes problem. Here's the building. Most houses are like that. You open the door. You are sitting outside. Cold. And you open the door. And then eventually you go inside, you close the door, and you are quite happy. Okay, let's see what happened. When the door was open and you were trying to get in, there was a transparency between the outside cold and the inside air-conditioned environment. So what happens is, during that time, again because of that transparency, as you're coming in, cold air is coming in, warm air is getting out, and you're wasting a lot of energy. Okay? So actually, you're walking into a room that, in a building that is cooler than what it was before you come in. That was because of this transparency. How do we solve this transparency issue in larger buildings? Okay, well, we solve it like this. We say instead of this is a larger building. Instead of one door, let's have 2 complementary doors. Okay. Again, you're sitting outside. Well, you're still unhappy because of the cold. And you want to get in. What happens is you open this door. As soon as you open that door, the door inside closes, or it's closed. Then you come in here. Okay? Then you come in here. But then the next step is you open the inside door, and then you come in here. But see, there was no chance, neither when the inside door was open or the outside door was open, there was no chance for the airflow to go one way or the other. Okay? And therefore you are actually walking into the place without really significant amount of energy being wasted. What did I do here? I used, in order to eliminate transparency of the air, I used two complementary doors. Why not? I do exactly the same thing in place of these transparencies that I have here. So that's what I'm going to do. I'm going to take a cross-coupled latch, just like what I did before. Another cross-coupled latch. And then use a complementary clock, meaning the door open, for the second one. And then this becomes my D, this becomes the master, this becomes the slave, and this becomes my Q. Now what happens when I give it the clock? Okay, when I give it the clock, clock becomes 1. Clock becomes 1. The D input goes halfway, means this situation here. Then when clock becomes 0, is this situation here, meaning that the front door is closed, the inside door is open, and therefore you are letting your D to go all the way to the output. But see, when your D is going all the way to the output, look at this diagram, this door thing on the right hand side. When the when this becomes here, okay, this door is closed. That means this left hand side door is closed. Okay, so what I have is really, this is like the inside door, this is like the outside door. This structure is called master, slave. I don't call it latch anymore, I call it flip-flop. And if I now use this flip-flop for my design here, for my counter really counts. Okay, I'm gonna do that. but I'm not going to show all the details of it. I will show a yellow box, which is the incrementer. I'll show a dark green box, which has my flip-flops in it. And then I have these lines going in. These lines going feedback. Incidentally, this when you wire 4 latches together with a common clock, this is called a 4-bit register. Same thing when you wire 4 flip-flops with a common clock, that is also a 4-bit register. Each of these boxes is a transparent latch. There is a clock coming into each one of these. And the clock is complemented to go into this. And then I have this incrementer here, which I'm gonna redraw this. Okay, notice that the delay for each one of these bits is different. Actually, the very first one has the smallest delay, equivalent to 1 gate delay. Actually, because of this is a constant, this input being a constant, this has very little delay going through. Okay, so let's say there is a delta delay here. And then here I have an AND gate and an XOR, so I have 2 delta, 3 delta, 4 delta. Okay, if I have a much larger counter, then the delays will all be different. What it really means is that it will be difficult for me to, if I were to do the latch thing, it would be very difficult for me to adjust my clocking when I have different logic delays for the different bits of my counter. That's beside the point. And what I have here is a clock input, and I also have that 1 up there. This if it is a 1, it actually counts up. If it is a 0, it doesn't count at all, and therefore this becomes my enable input. These are my count outputs because of the way the XORs are used. This is Q0, Q1, Q2, Q3. and this is following my flip-flop structure. This structure down here, which is a master-slave structure. Instead of drawing these two structures like this, actually it's like this. Okay, master slave, master slave. Instead of drawing them like this, I can do this. My clock is a pulse. That means a pulse is needed, and this is a C1, 1D. Okay, some draw it like this, and then I'll show you a different symbol, a more standard symbol later on. This edge here means that it requires the 1 to 0 transition of the clock for the input to be taken. All right. And this is a master slave D flip-flop. This is structure, or master slave D flip-flop. All right. Very good. And I want to do a few more structures before we finish this. And one is, let's look at this structure that we have been playing with, or the new structure that we have come up with. Remember I said that the two outputs are always complementary. So what it means is I don't really have to have an inverter going into the lower gate. Why can't I just take the other output and feed it into the input of the next one? Because these two, this one and this one, are complementary anyway, so there's no need to do the input. And okay, and then I'm gonna do this. Plus that I don't want to have a D flip-flop. I want to go back to my SR clocked, not latch anymore, SR clocked flip-flop. Well, this is good. Even though we've been talking about the D flip-flop, but still there are situations where you want to have something to put some data somewhere, saying set. Something wants to pick up the data, says okay, reset. That means the data has been removed. So it's a kind of handshake in between two different systems, which is good. Which is good to have something like that. The only problem with this is the 1-1 value. If my S and R become 1-1 at the same time, and you clock the circuit, then whatever memory you had completely is gone, is erased. Okay. Let's look at a way of correcting this. First of all, this is the problem I have with my SR. SR, and then the clock, Q plus 0, 0, 0, 1, 1, 0, 1, 1. If the clock comes in, or actually, to show you the new notation, this. That means when the clock makes a 0 transition, 0 0 doesn't change, 0 1 will set it to 0, 1 0 will set it to 1, and 1 1 we are back to the situation where this is bad, this is not allowed. I'm going to do this. I'm going to look at the situation when my existing Q is 0. And my existing Q bar is 1. Okay? What it means is my circuit is reset. Okay? If my circuit is reset, the reset input is really not effective anymore. Okay, see, if my output is already 0, reset resets it to 0, but this is reset already. So there is really no need for resetting it after the output is already reset. With this being said, I don't think you have any complaints if I take this output, bring it back here, take this output, bring it back here, and put it into this gate. Why not? Because it's a 0, and reset, there is no use for reset anyway. And what I did, I took that 0 on the outside and masked this AND gate. Remember, this is an AND gate. An AND gate, which means that if one of the inputs is 0, it doesn't allow other inputs to propagate. But that doesn't cause me a problem because I don't want, because even if reset propagates, it's not going to change anything anyway. Okay, so I had done no harm by this orange feedback line. Now let's look at another scenario. What if I have a 1 here, a 0 here? This is this situation here, where my output is 1. Okay? When my output is 1, my circuit is already set. I cannot set something which is already set. So you shouldn't complain if I take this 0 from here, feed it back here, and put it into this gate. I put it into an AND input, and because it's 0, it's not going to allow S to propagate. Well, that's fine, because S is already, my circuit is already set. I cannot set something more than set. Or I cannot reset something more than set in the orange case. Okay? So, in effect, I haven't done anything wrong. But now let's look at this. What if I have a... let's go to the orange case. What if my circuit is reset, that means it's orange, and then I put a 1 here and a 1 here. The orange feedback doesn't exist for the upper input, and therefore this one is going to go through as a 1. But then this one is prevented from going through because there is a 0 feedback, and therefore this is a 0 here. So the internal set is 1 and the internal reset is 0. Even though the clock was there, but then the internal set is 1. Okay, the internal the reset was prevented by the value of the output, and therefore after the clock with 1 1, this changes to 1 because it is set. Okay, so when it is it is reset, and 0 changes to 1 for SR11. What if SRR11 and the circuit is in the set state? It is in the set state. The blue line feeds back, brings in a 0, and prevents this one to go through, and therefore this becomes 0. On the other hand, the 1 on R, because there is no 1 to prevent it from going through, it goes here and becomes a 1 here. So in the case that my circuit is set, I am bringing a 0 into the set, a 1 into the reset. So 1 1, a 1 in the reset changes this to 1, and therefore 1 1 changes the output 1 to 0. Okay, I just solved my problem of having 2 1s that erase the memory. Having 2 1s in this circuit now doesn't erase the memory. It actually, if Q is 0, it makes it a 1. If it is a 1, makes it a 0. What it means is that my next Q is Q bar, and therefore this I put a Q bar here. This is so good that I'm gonna give it a new name. I call it JK flip-flop for jump and kill, and I'm gonna call this one J, I'm gonna call this one K. Okay, and this is a JK clocked master slave flip-flop. Okay, and then this has a characteristic equation as well. Okay, let's look at this. J, K, Q. This is Q plus 0 1 0 0 0 1 1 1 1 0. Look at the first column. The first column says that JK is 0 0, and therefore nothing is going to change, and therefore this is 0 1. Second column says JK is 0 1, means that I'm killing it, and therefore it's going to be 0. The fourth column says JK is 1, that means I'm jumping it, so it's 1 1. The third column says 1 1, that means it's complemented. 0 becomes 1, 1 becomes 0. Q plus becomes JQ bar, ORed with K bar Q, and this is the characteristic equation for the JK flip-flop. This is the transition table for the JK flip-flop. Alright, we have seen the D flip-flop, we have seen the JK flip-flop, and I'm gonna do one little thing or two little things and then go. The JK flip-flop, notice, let's do it right on this. Well, let's do it here. I have the JK and the clock and Q plus 0 0 0 1 1 0 1 1. Nothing. 0 1 Q bar. And this is this structure here, J K 1, 1 means controlled by the clock, and then this is the C1, and this is Q. Okay, I'm gonna tie these two together. If I tie these two together, it means that J and K can never be different. Therefore, I either have this, I'm eliminating this and this. I'm going to call this one T. And therefore, this table changes to this. C, T, T0, Q plus becomes Q, T1, Q plus becomes Q bar. I'm calling this a toggle flip-flop. That toggles. Actually, I can build same thing with a D flip-flop. If T is 0, means that the XOR is just taking Q, feeding it back in. But then if T is 1, it means that with each clock you are toggling it. By the way, a toggle flip-flop is a 1-bit counter. Okay, we will get to that later on. And let me do one last thing, and that is, this is the circuit we had. Remember this? For now, let's do the D flip-flop. Okay, or the D latch. I like to change this to all NAND. I take this bubble. Remember, this is D, this is Q, and this is Q bar. I take the, to turn this circuit into all NANDs, I put a bubble right on this output. That becomes NAND, but then I have to make up for it by putting a bubble here. I put a bubble here, make up for it by putting a bubble here. The two gates on the output are half NAND. So I'm going to take that bubble, this bubble here, move it along this line and put it here. Okay, if I move this bubble from where it is along this line and put it over here, good, I have already turned my node, the lower node, to two inverted inputs, and then I've got rid of this inverter or this bubble that I don't like inverters on the output of the OR gates when I'm turning all things to NAND. I like inverters on the inputs of the OR gates. But see, removing this changes this to Q bar. I'm going to do the same thing with the lower bubble. I'm going to take the lower bubble and place it right over here. Again, if I do that, this is gone, and then Q bar becomes Q. Now my circuit is all NAND, but then the good thing about this is I can put Q and Q bar where they were, and then remove this crossing here. Okay, and therefore this circuit is exactly a clock, this clock. This is a cross-coupled NOR functionality with AND gates. So this is a clocked the latch, and then you can go back and change all of these structures to all NANDs. Alright, we're going to continue with this, and we're going to do more structures and more very long as well. We haven't done much very long, even though look at this, for example. You could to build this, you could take two of those always statements and put them next to each other, and that would be a D flip-flop, something like this. Let's say reg M comma Q, and then you say always at D comma clock if clock Q gets D, then you have always at D comma clock bar if clock bar, sorry, not D, not Q, okay, and somewhere assign clock bar equal tilde clock. This works. Okay, but we're gonna do better than this. And this is the very long description where this is I'm calling M, this one I'm calling clock bar, and this of course is SR. So let's go back. This one, yeah, this is M, and this is clock bar. So the very long description corresponds to this structure here. And let me do this. Okay. All right. This is the end of it. This is the first lecture on memory elements. Talk a little bit about flip-flop timing. See, when we had master-slave flip-flop timing, when we talked about master-slave, it was the situation where whether you are doing D flip-flop or the JK or whatever you're doing, the clock is treated as it's after the clock becomes 0. I don't say it's falling edge, I say after clock becomes 0. Okay, the way the structure is that when the clock becomes 1 and then the clock becomes 0, you have the required time for the clock to become 1 to propagate halfway, and then you have the required time for the clock to become 0 to go the other half and then appear on the output. This is the timing for the master slave flip-flops, okay, for the master slave. And why is it that we did not like this? Well, we don't like this flip-flop because it requires that blue amount of time for the data to go halfway, and then it requires that orange amount of time for the halfway to go forward into the output of the flip-flop. So we said, well, let's, instead of doing that, let's come up with edge trigger flip-flops. With the edge trigger flip-flop, what happened was we did this flip-flop, and then we are not going to go look inside it, but then we said something like this: my clock okay, this is edge trigger. Whether it's rising edge or falling edge doesn't really matter, but then the key thing in this was we said that both taking of the inputs and putting it half in the middle is done as the clock is making a transition from 0 to 1, and then as the clock is making a transition from 0 to 1, the other half is also becoming active. Actually, the two things that I'm showing here happening on two levels of the clock, in the edge trigger, they happen on the same edge of the flip-flop, and therefore something like this. If I show the flip-flop like this, timing wise, it really looks like this. This is done the last part of it, and this is done the first part of it. Okay? And therefore I claim that this is a faster flip-flop. Okay? And it is, because the edge is a lot quicker than, or this ramp, this rise time is much faster than having to wait for the 1 level and then having to wait for the 0 level. Even though I say that, but then we shouldn't forget that there is still some timing constraints. Okay? What are the timing constraints? The timing constraints are this. For a D flip-flop, I cannot change my input too close to the clock. Or, actually, I cannot change my input too close to clock rising or too close to clock changing. And after the clock has changed, again, I cannot change my data so quickly. So this is how I defined my timing. I say that I have a data signal. I have a clock. For a flip-flop that is, let's say, rising edge. This is my clock, and then I have this data here. I say that for the proper data to be captured by the active edge of the clock, I have to, when my I have to allow my data a setup time. What it means is, just before this, kind of like this, okay? my data. If it's want to change, fine, it can change, but then it cannot change in this region here. So what I'm saying is I want to allow a setup time. And if it's too close to the edge of the clock, what it means is that I'm not allowing the setup time. I'm not allowing the new value of the D input to propagate into this structure. Think about the structure that we were talking about. To propagate into this structure so that the clock will effectively take that data and put it on the output. Okay? I'm not going to go through, actually we never go through all the details of the timing for the D flip-flop, but we just say that if you are operating a flip-flop, you have to follow the setup time. Don't close your data, don't change your data too close to your clock edge. Okay? This timing, I'm calling it setup time. T setup. That's the time required for the data to set up before it's clocked. Okay? So let's say I did not violate the setup time, everybody is happy, and my data is continuing and everything is good. Okay? And a few clocks later, the same thing, my data input is still a 1. And again, I did not violate the setup time, and then the next edge of the clock arrives. Okay? I'm going to say this. Well, the same way you allowed a setup time before the clock, you also have to allow what is called a hold time after the clock. What it means is this new data that was just captured on the edge of the clock cannot just change immediately after the edge of the clock. Cannot just change immediately after the edge of the clock. Okay? Actually, you have to allow, what should I call this? A hold time. And therefore, T hold. So what it means is every flip-flop, every edge trigger flip-flop has this timing given to you. If you look at 7474, that's old technology, the 74 LS74, then it gives you a setup time, a hold time. Every flip-flop you look at, even if you look at the flip-flops in your FPGA library, it gives you a setup time, a hold time. See, these are not real. These are actually, you cannot extract it from the transistors and all that. These are experimental. Okay? It says that allow this much of time for the setup time and allow this much of time for the hold time. And therefore, when you buy a new flip-flop, it gives you actually several different things. It says clock frequency cannot be faster than this. Setup time is this. Hold time is this. Okay? And you have to follow this if you want your flip-flop to work properly. All right. Something else about the flip-flops which we have not seen before, and that is NMOS or CMOS flip-flops. Okay? The master slave flip-flops that we developed, they are cross-coupled gates. But instead of that, I can have an inverter with a switch . This is my clock, and this is the invert of the clock. Actually, this structure sorry, this structure is like a latch, because if C is 0, let's say if C is 1, if C is 1, it is transparent and D goes to the output. If C is 0, this switch is cut off. If that switch is cut off, I am relying on the input capacitance of this gate. And that is a good capacitance and holds data for some long time. Okay? So it is a latch. It looks like a latch. The only difference between this and the latch is that latch also gives me the true output. This only gives me the complemented output. However, it is like a latch. When C is 1, it is transparent. In this case, I am putting two latches together. Oh, by the way, this is called half register. In the upper diagram, I'm putting two of these half registers together with complementary clock. Well, that's the same exact thing we did with the latches for master-slave flip-flops to build a the master-slave D-type flip-flop, right? That's exactly what we did there. And now the structure I have here, if C is 1, if C is 0, if C is 0, okay, then this path is disconnected, but then this path is conducting. When C becomes 1, then this path is disconnected, this path is conducting. Okay, actually this goes this far, and the other one goes this far. Okay, and therefore we do have that a removal of transparency that we had problem with in the latch. The beauty of this is it only uses 6 transistors, but then there are other structures that use the same thing. There are other structures with few transistors as well. Then there are other CMOS structures, but I just wanted to show you that not all master-slave flip-flops are necessarily built by those cross-coupled structures. Okay, but when you do edge trigger, you really have no choice but to go to that big hardware, that structure there. The problem with this is again the problem we had with the master-slave here, which is you have to give it a time for it to go on and then off. And also there is also a problem that because of the inverter in the clock, if you have overlapping, then there will be a short amount of time that because of the delay of the inverter, there will be a short amount of time that both of them are conducting. So there will be a short amount of time that you do have transparency, and for that they do non-overlapping phases of a clock. I'm not going to get into that. All right. So that was flip-flop timing and CMOS or the transistor level flip-flop as well.